Thank you, everyone. As you heard, my name is Fabio. I am a grad in 2022, and today I'll be talking to you about Turing machines and the birth of computer science. Okay, so to get right into it, first I'm going to present to you the problem to which the solution is Turing machines, and then I'm going to be going over how they work, the capabilities of Turing machines, and then I'm going to be getting into the concept of Turing completeness. Then I'm going to give you some examples of Turing completeness, such as a computer built inside of Minecraft, the game, Rule 110, and HTML and CSS being Turing complete, and the implications that come along with that. And then I'll conclude the talk, and any questions can follow. Cool. Okay, so to set the stage, World War II has started, and a set of mathematicians led by a man named Alan Turing are tasked with solving one problem, and that problem was to decipher the Nazi Germany's encrypted communications. That's Alan Turing, by the way. So to encrypt their communications, the German used a machine called Enigma that plugged into a typewriter and scrambled the input according to certain settings on rotors. So the reason this was difficult to crack is that Enigma had a lot of different ways it could scramble inputs. So it would take input and scramble it according to the settings on a rotors, and it would produce output. Now, the amounts of different ways that Enigma could scramble input was 159 quintillion different ways. Okay, now that's a big number. So to visualize how big that number is, if it took 10 seconds to test each case, it would take 100 people more than 500 million years to crack the encryption. So feasibly, you cannot do that by hand. And they only had 30 people to get it done. And they had to get it done in 24 hours because the settings on Enigma would be changed daily. So they needed to come up with a new plan. So to solve this problem, Alan Turing and his team decided they're going to need to figure out how to do it faster. And the only way to achieve this speed was to get a machine to do it. But not just a normal machine that existed already, because all the machines at the time were single purpose, and a new one had to be built when a new problem came about. So what they wanted is something that was capable of taking in a set of instructions and producing some kind of output. So today we know this as a general purpose computer, but back then it was known as an implementation of a Turing machine, and it didn't exist yet. So what is a Turing machine? A Turing machine is an abstract machine that manipulates symbols on a piece of tape according to a set of rules. Simply put, it's a machine that if you know how to speak to it, it can do anything you want, literally anything. So it's made up of three things. It's got a tape, a head, and an instruction set. So there's a picture of it. The tape is just a string with a bunch of characters on it, and the head reads the current character on the string. And then inside that little box underneath, it's got an instruction set, which basically tells the head what to do when it's reading a certain character. Okay, so what can Turing machines do? They can do anything. They can do anything computable. Now, what do I mean when I say computable? Computable just means that something is computable if it can be described by a well-defined set of rules. Something like a recipe or an algorithm, anything that can be described by a step-by-step process. So if you can describe it linearly and it's got a bunch of steps to it, it is computable, and pretty much anything that you want to do can be described by a set of steps. So Turing machines can do anything, which also brings us to the concept of Turing Complete. Now, something is Turing Complete if it can be used to solve any computational problem. That means Turing Complete means a system can do anything. So some examples of Turing Complete systems is any other modern programming languages we use today, such as assembly or C, C++, Python, JavaScript, SQL, Bash. Those are also Turing Complete because they can conditionally branch and loop. There are also some unexpected systems that are Turing Complete as well, such as the C++ template system. That subsystem of C++ is Turing Complete. So in essence, C++ has a programming language embedded inside of it. So it's the best language. Also, Minecraft, Turing Complete, which I'll get to soon enough. Microsoft Excel, Conway's Game of Life, Rule 110, Magic the Gathering, the card game, Minesweeper, that game on your computer no one knows how to play, and HTML and CSS. When you put them together, it is Turing Complete, but I'll also get to that in a moment. So here's an example of a computer being built inside of Minecraft. This person was able to build games on their computer. So in essence, you've got games running inside of a game, running on side of a computer, and they're all just Turing machines. So it's a little bit recursive in nature. And this person was capable of building Snake, Tetris, Pong, Breakouts, and they're also capable of building a graph rendering engine. So they're able to plot functions such as parabolas and circles, hyperbolas, all of that. Yeah, so there's also be able to build Connect 4. And the graph rendering engine, as you can see here, which is pretty cool. So you don't just get toy examples, you can actually use it. Although building something useful in that requires a lot of power. So if you got a decent computer, give it a shot. Also, next example of Turing completeness is Rule 110. So imagine you've got a grid, a one-dimensional grid of blocks, and each block has a state, either on or off. And well, the nature of a one-dimensional grid, you've got a left neighbor, and you've got a right neighbor, and you've got yourself. So you see the pattern of on, off, on, or on, and from there you decide your next state. So when drawing Rule 110, you draw the first state, and then the state after that, and so on. So you've got a sequence of states, and it produces this two-dimensional grid. And it actually creates quite a cool picture. So this is an implementation of Rule 110 that I did. It's a bunch of triangles that get produced by the certain set of rules. And the whole idea is that with these set of rules, you can create machines that can add, they can count, they can multiply. And once you can do that, you're capable of doing anything. It's just processing power. That's the question. So the main reason I'm showing you Rule 110 is that this Rule 110 can be implemented in HTML and CSS without the use of JavaScript. And here is the code example of it. So the CSS really just handles toggling of inputs, which is in the HTML file. And the HTML file is 900 lines of exactly the same line. It's just an input tag with type equal to checkbox. And that just handles on and off. But this just shows you how HTML and CSS is capable of running Rule 110, which is Turing complete. So by transitivity, HTML and CSS is Turing complete and is a programming language, although it just doesn't scale well, because to create a toy example of Rule 110, you need 900 checkboxes to handle 15 blocks, which isn't plausible. Okay. So to conclude, after months of building his Enigma-beating Turing machine, Alan Turing was successful, and his machine helped save the lives of approximately 21 million people, and it helped win multiple critical battles in World War II, as well as shorten the war by 2 to 4 years. When the war was over, the British government recognized the power of Turing machines, and they invested a lot of resources, time and people into investigating Turing machines, and they later became known as general purpose computers. And so out of war and conflict, computer science was born, and along came the age of technology. So here's an image of the first Turing machine that was built. This is the one that broke Enigma. That beat Enigma. So it's a little bit more complicated than the tape head instruction set image that you saw earlier, but this is what it takes to build a Turing machine with the use of electricity, and I think vacuum tubes, I'm not sure. But yeah, Alan Turing nicknamed this one Christopher. He named it Christopher after his late best friend. And yeah, if you'd like any more extra information on Turing machines or Alan Turing himself, there is a book called Alan Turing the Enigma. It's on Amazon. And there's also the movie The Imitation Game on Netflix. Most of them focus around Alan Turing himself, but there is some detail on Turing machines, as well as you can search up any textbooks on Turing machines if you'd like to investigate that. And I've linked my GitHub because I've got some examples up there of Turing Complete systems, such as Conway's Game of Life or Rule 110 that you can pull down and play around with, break, change the rules, see what happens. Yeah, thank you.